Great. So I would say thanks everyone for connecting today. We are ready for another great afternoon, well, afternoon for me, for discussions, and maybe morning or evening for people around the world. So it's a pleasure to start with Andrea Ferrara from Scuola Normale Superiore. And Andrea, the stage is yours.
Thank you very much, Anita, and good day to everyone. Today, I would like to discuss about the interstellar medium of the high-redshift galaxies. So, first of all, it's a pleasure to be here at the SAZERAC meeting and discuss this thing with you, even though just virtually. But what I would like to do is just to concentrate on a particular epoch during the cosmic evolution, that is the epoch of cosmic reionization. And we would like to know what type of sources, what type of galaxies were populating those very distant, very remote epochs. So I have a problem in advance. Yeah, I should do this maybe. Okay, so what do we know about epoch of reionization galaxies? Well, we have some information that is mostly coming from statistical surveys in terms of for example, the luminosity functions or the UV luminosity of these galaxies distributed, or we know how the stellar mass density evolves with time. Interesting also is the star formation rate evolution as a function of redshift, so how many stars are formed per unit volume. And also there is indication that the size of these galaxies is evolving. But so far, we have collected all this information, but we don't know much about the internal physical properties of these galaxies, of these systems. Are they the same as those at low redshift, or do they differ? Is there an evolution also in their physical properties? So one of the questions, before I address the actual problem that I want to talk to about the interstellar medium, I think that there is another question that has only been slightly touched upon, so we don't know very much about the presence of AGNs in at least some of these Lyman break galaxies that are selected through the Lyman break technique, and particularly in the luminous one. Clearly, we need to answer the question in order to understand the evolution and the formation of supermassive black holes, but because we think that the progenitor of these supermassive black holes can be or might be hidden in luminous Lyman break galaxies. So far, we have predictions that are just showing that if you look at these two panels that represent essentially the UV luminosity function of galaxies and black holes and the sum of the two, then you see that, for example, depending on how you seed the primordial black holes or the very first black holes into galaxies, you may have different answer, but not so much that the two cases that I'm showing here on the left, a very efficient seeding case, another one inefficient seeding case, produce considerably different results. But in particular, if you concentrate on the right panel, that is, in my view, is the most physical one, then you see that the black holes start to dominate the UV luminosity functions for luminosities brighter than minus 23.5, where we do expect to see an AGN fraction of about 1. So these are what we usually call the quasar population. But even if you go down to magnitudes of minus 22, still 1 in 166 galaxies is supposed to have to host a black hole with masses of the order 10 to the 7, 10 to the 8 solar masses. So this may have very important implications for the properties of galaxies. And how can we know if this is true or not? How can we test this hypothesis? Well, for example, using UV lines to identify these AGNs. And there are already some attempts that are suggesting that this could be a very interesting path for the future. There's one example that I'm reporting here, the case of the galaxy COS-Y located at redshift 7.15, in which we have detected, actually Laporte et al. Have detected a prominent nitrogen-5 line, which has a flux that is at reach of many or some future missions like the Atlas Probe Deep, or of course also JWST. Now, this line is in particular is a tracer of AGN activity because its potential ionization potential is pretty high, and so it cannot be produced by stars, or at least not stars that have an IMF and the metallicity that we think of. And so by building these diagrams and with combining these UV lines and also carbon-3 1909 and carbon-4 and so on and so forth, then you can build this type of diagrams in which you can actually determine whether the galaxy is indeed hosting an AGN. And that would be a tremendous advance for our understanding of the supermassive black holes, and also the contribution of these black holes to cosmic reionization. So, but of course, the main instrument to study the interstellar medium of these high-redshift galaxies, so the internal properties, is definitely ALMA, and soon also JWST. But ALMA so far is what we have, and so we have some results that are flowing in that are really very interesting. So one of the major issues that people are worried these days concerning the interstellar medium and the emission of far-infrared lines from galaxies in the EOR is through the use of the carbon-2 158 micron far-infrared line. And so we now have a decent sample of this sources located into the reionization, towards the end of reionization. And so we can build plots like this one, in which we compare the carbon-2 luminosity, the line luminosity, compared with the star formation rate of galaxies. And we can also color code this emission in with the equivalent width of the Lyman alpha. Well, one thing that is very puzzling compared to the local similar relation measured by the Lise et al. In 2014, then we see that many galaxies, particularly those with large Lyman alpha equivalent width, seems to show a deficit, so they are carbon-2 deficient. So this might hint of some interesting physical processes, the process that is going on inside these galaxies. And so many people have tried to give an explanation for this deficit. So most of the explanations are based, but not only on numerical simulation like this one that we are seeing, in which we are just simulating one of these galaxies that we are observing with ALMA at redshift 6. And so you see that in order to resolve the physics of the interstellar medium, you need to have very high resolution. You're going around 10 parsecs. And also you also need to, among other things, also include the effects of dust and the radiative transfer on the fly. So these are rather expensive simulations, but then you can really afford to go down to the very center of the galaxy. And to our surprise, we see that many of them show these structures like the one that you see here. And so these galaxies tend to have a disky, well-organized disk, rotating, well-organized disk, which nevertheless is relatively compact. So these galaxies have sizes that are very small. Typical effective radii are of less than a kiloparsec or even half of a kiloparsec, but nevertheless they are already considerably enriched. So the metallicities are already in the range of 0.1, 0.5 solar, contrary to what you would could naively expect for a high-redshift galaxy. So the enrichment process is very rapid. So with this simulation, you can also compare to the data. And so you see that the clumpy structure that you see in the simulation is also seen in when you look at carbon-2 velocity channel maps or another galaxy. This is galaxy WMH5 or redshift 6. And you see that if you scan through the channels, then you see that the different blobs are coming and going. And so that means that these galaxies are indeed clumpy, even though they show a disk, and I'll come back later to this point. Now, one thing that you need to keep in mind while you're trying to model the carbon-2 emission from this high-redshift galaxy is that the CMB is on the way, because the CMB tends to populate the atomic levels of the carbon atom in such a way that they are in thermal equilibrium with the radiation itself. And so in that case, there is no contrast between the emission and the CMB, and so the signal disappears. This is particularly evident in this figure when I'm showing in the top panels a galaxy, a simulated galaxy seen face on, and the bottom panels are seen edge on. And you see that while the carbon-2 ion surface density is rather extended, so it can extend to several kiloparsecs, then the carbon-2 line emission, when you transform this physical map into an emission map in carbon-2, then you see that 1/3 of the carbon-2 mass that resides in diffuse low metallicity is essentially suppressed. And so it's only the dense central parts that are co-located with the molecular hydrogen disks that are contributing to most of the light that you see. So the CMB is really cutting off at least the edges and the low density region. So this is an effect that you need to take into account, and at the same time it also affects the luminosity of the galaxy itself. But when you do the simulation and you account for these effects, then this is what you get. So this is a simulated version of the sigma carbon-2 versus sigma star formation that is obtained from the simulation, and this is the local relation. So you see that many of the galaxies tend to be carbon-2 deficient, indeed, as observed. And so when we look at the simulation and we ask the simulation, so why are these galaxies deficient? So we look one by one, the galaxies that show this feature. And so we concluded that galaxies that are carbon-2 fainter tend to be starburst, and the starburst galaxies have relatively less emitting gas compared to their star formation rate. So the star formation rate is too high for the amount of gas that is available to emit the carbon-2 line, and therefore they tend to be fainter. And metallicity is also part of the game. It's not negligible, but it plays a subdominant role. So it's just the main reason is that these galaxies essentially are located above the Koenig-Schmidt relation, so they tend to be starburst, and that depresses the carbon-2 emission. But this may not be the only reason. In fact, there is also an issue that we discovered that has to do with inclination. So if you take a galaxy, a simulated galaxy, and then you look at the line profile, the carbon-2 line profile, as you rotate it, then this is what you're seeing. So as you are moving the galaxy to be seen edge on, then you see that the two typical peaks that denote rotating disk appear, but then the overall intensity of the line decreases. While as you move the galaxy, rotate the galaxy toward the face-on position, then the intensity of the line grows and becomes single peak. So it may be that inclination also can play a role in the deficit issue. So this is something that we are currently investigating in even more detail. Clearly, once we will have JWST up and working, then we can also study the dynamics of the and also other phases of the ISM through the H-alpha emission maps like this one, and so you would clearly see the position of super H2 regions around stellar clusters that can be resolved probably with JWST. So this is really a very exciting perspective. So one of the reasons for which we like to study galaxies in the EOR is also because we would like to witness in the assembly of galaxies in action. And so this is a sequence of a time sequence of a galaxy, a simulated galaxy from redshift 7.2 to redshift 6. And you see that there's intermittent changes in the nature and the morphology of the galaxy. So you go from very clumpy and disturbed situations, like for example, this one at 6.38, to very quiet and nice, well-organized disks. So whether the high redshift galaxies are disks or are just clumps that are merging in a very violent way may depend on the phases at which you're observing the galaxy. And so it's not a surprise that both type of examples are being found from observations. So we have examples of nice rotating disks, like the one, like the picture on the left. And also we have examples of very clumpy structure, like the one that I showed before, but also additional examples are reported here in this paper by Carniani et al. 17. So you see that this is something that resonates with what we find in the simulation, and we see that this truly the merger rate is dictating the morphological changes that we can observe at relatively short time lapses. So having said that, assessing whether these clumps are there and these clumps, what these clumps that we see in the carbon-2 are made of, is something that we can address with JWST. And so in particular, we would like to know whether the clumps are internal clumps produced by for example, gravitational instability that is leading to star formation, or they are satellites orbiting the galaxy itself. So this is an overall view of what JWST and ALMA could do, and also HST, of course. So we have produced mock images in all these bands from band Z down to the carbon-2 band, and then we produce also, we convolve this with the PSF, 0.15 arcseconds, and then we produce a surface fit. We remove the main galaxy, so we are left with the residual that you show that you can see in the fifth column here. And so the exercise shows is a feasibility study that shows that indeed, particularly with JWST in some specific bands, and also with MIRI, we can, in principle, observe these clumps and determine their properties very carefully. So this is, again, another interesting perspective. So we will be able to see whether these clumps have an internal origin or they are related to satellites. Note here again that we predict that the carbon-2 usually, we always find that the carbon-2 is more extended than stars and dust. This may be an indication of an outflow from the galaxy itself that is spreading the carbon-2 in the circumgalactic and intergalactic medium. Just to finish up, I think that the combination between the JWST and far-infrared lines from ALMA is very promising in the sense that, and I want to show an example in which this type of studies can already be done right now. So this is another galaxy COS-Z1 for which we have a detection of the carbon-3 1909 line, but it's also been detected as spatially resolving in carbon-2. So this galaxy is, again, carbon-2 deficient, even though not so much. And so if you can have the information from the carbon-3 line, which traces ionized gas, and the carbon-2, which predominantly traces neutral gas, then you can indeed obtain a lot of information, as I going to show in my last slide. I'd like to mention, though, that this line is very interesting because if you're observing, say, in the range between 1 and 4 microns on Earth, then you can follow this line through a very large span of redshift, or redshift 5 to 20. So this is really an ideal line to follow up high redshift galaxies. So if you have these two lines, what can you do? You can do something very interesting, because Livia Vallini has developed a model that combines, a physical model that combines the information from these two lines to obtain different physical properties of the interstellar medium of the galaxy itself. For example, this is what happens if you apply our method to these galaxies and we determine the physical properties. For example, we are able to determine metallicity with quite a good accuracy, and in this case we find it's half solar. We can determine whether the galaxy is a starburst or not, and in this case we find that it's slightly above the Koenig-Schmidt relation, and also the mean gas density that we can see from the likelihood is very well determined. So this is just the proof of concept that the method can work, and whenever we will have JWST, of course, we can apply this to many galaxies and determine, for example, things like the mass metallicity relation and the amount of the occurrence of starburst in this very high redshift systems. So I'm done. I'm just coming to my conclusions, and so I think that spectroscopy is fundamental to obtain the physical properties of the interstellar medium, and therefore also to study star formation in early systems. And also to assess the presence of faint AGNs in line-of-break galaxies. We are starting to understand the carbon-2 deficit, maybe is related to starburst activity. And also we can study the galaxy assembly and dynamics in a very, in a way that was impossible until a few years ago. This is very interesting because you can also study rotation curves, dark matter, and so on and so forth in these pristine systems. These clumps, we can assess whether the clumps that we see are due to gravitational instability, or if they are due to satellites orbiting the galaxies. And the combination of far-infrared and UV lines will allow us to study in very much detailed physical properties that otherwise would escape our understanding, and therefore would prevent our full study of the interstellar medium of these pristine systems. Thank you very much.
Thank you, Andrea, for the very interesting talk. We have a few minutes for questions. So Angela raised her hand.
Thanks a lot, Andrea. Do you hear me?
Yes, I do.
Yeah, that was a very interesting talk and plenty of things to think about. But as a question, so about the giant clumps, I do not understand. So we will detect these clumps, but how we will understand if they are in situ satellites? Is there a criterion that you are thinking of? I mean, we see the clumps around the bulk of the luminosity, but then how do we decide if it's in situ or a satellite? Is a distance? I don't know.
Yes, it's of course it's a very good and at the same time very difficult question. I think that one possible way to determine whether they are internal or external would be to at least in a statistical sense, we know that, for example, the metallicity of galaxy of the central galaxy is different from the one of the satellites. And from simulation, we can indeed find that the two distributions are separate. And so, if we are able, for example, by combining far infrared and UV lines to determine the metallicity of the two clumps, that would be definitely a way to discriminate between the two cases. And satellites are also probably tend to have a star formation which is a little bit more bursty with respect to the central galaxies. Of course, it's not easy. I don't know, maybe we have to think more about that. Actually, any idea would be useful, but so far, the metallicity seems to me that is the best tracer.
Okay, thanks a lot.
Thank you. So I'm afraid we are running a bit short on time, but I encourage all of you that still have questions to post them on Slack, and then maybe Andrea can answer to you there on the Slack channel.
Absolutely.
So thanks again, Andrea. And I think we can move on to the next speaker, Joo-Hyun Lee from UT Austin. So please feel free to share your screen. Yeah, perfect.
Yeah. Hello, everyone. Nice to meet you. My name is Joo-Hyun Lee, and I'm a first-year graduate student at the University of Texas at Austin. So I'm going to present my research paper that I wrote with Eunjin Shin and Ji-Hoon Kim when I was an undergrad student at Seoul National University. So for more information, please refer to the journal or archive number at the bottom. So in the typical lambda-CDM cosmology, dark matter builds the skeleton of baryonic structures like galaxies and galaxy clusters. So naturally, therefore, most galaxies that we can observe contain a great amount of dark matter. However, Van Dokkum et al. 2018 found that NGC 1052 DF2 and NGC 1052 DF4 ultra diffuse galaxies, UDGs with stellar mass of about 10 to the 8 solar mass located nearby a giant elliptical galaxy, NGC 1052, have only little dark matter. So this mysterious small fraction of dark matter make them to be called dark matter lacking galaxies or dark matter deficient galaxies, or DMDG. So those small fraction of dark matter cannot be explained by the conventional galaxy formation theory in the lambda-CDM cosmology. So we are going to explore how this could be possible. Okay. Yeah. So also observations performed by several groups show that NGC 1052 DF2 has another interesting characteristics. So it has unconventionally bright population of global clusters. And GC population has a peak at -9 magnitude, which is which is about 1.5 magnitude brighter than typical Milky Way global clusters. And size and ellipticities are also very large compared to the typical Milky Way GCs, global clusters. So in these plots, you can see in this plot, you can see the luminosity function of the global clusters. And in this plot, you can see luminosity and size of the global clusters of NGC 1052 DF2. Oh, sorry. So to address those enigmatic properties of NGC 1052 DF2 and DF4 and its member global clusters, lots of researchers suggested various formation scenario. In my work, we demonstrated a scenario suggested by Professor Joseph Silk. So he suggested that a high velocity collision of two gas-rich dwarf galaxies, an event that is comparable to the famous bullet cluster, can produce dark matter diffusion galaxies. So some people call this event as bullet dwarf. Because dark matter and stars are thought to be almost collisionless, when two galaxies collide with each other, dark matter and stars will just pass through, but gas will experience significant ramp pressure and then will form shock like here and produce dark matter diffusion galaxy after the collision. So this is our simulation setup, and we start with dwarf galaxies with total mass of 5 times 10 to the 9 solar mass. Then this is from our, oh sorry, I think my movie isn't working. Oh yeah. So this is our first paper that showed dark matter diffusion galaxies can be produced during high velocity collision of dwarf galaxies in 80 parsec resolution simulations. So our results showed that these circle dark matter diffusion galaxies have about 10 to the 8 solar mass, stellar mass, and a very little dark matter. And in my work, we re-demonstrated the formation of dark matter diffusion galaxy with significantly enhanced resolution of 1.25 parsec. So as you can see in this area, 80 mega year after the collision, star clusters are orbiting this dark matter diffusion galaxy, and stellar mass of the dark matter diffusion galaxy is about 3 times 10 to the 8 solar mass and has almost no dark matter. And so 80 mega year after the collision, 42 bound star clusters are found, and those star clusters are being realized as shown in this middle plot, so which is a key assumption of dynamical mass estimation in observations. And also this movie shows how and where stars in star clusters are produced. The key for the efficient formation of star clusters is gas compression by collisional shock during the collision, and surface density of these gas clumps are higher than 1,000 solar mass per square parsec, which leads to very efficient star formation and also massive star cluster formation. So this figure shows that dark matter diffusion galaxy and massive member star clusters are formed simultaneously within just about 150 mega year, and each massive star cluster is formed within only 50 mega year. Here is an analysis of star cluster properties and comparison with the observation. We could demonstrate the formation of massive star clusters, which can be connected to observed bright population of member global clusters of NGC 1052 to DF2 and DF4, and stellar mass of those massive star clusters and other star clusters is between 10 to the 5 to 10 to the 6 solar mass. And the most massive ones here denoted with star SC1 to SC5 have more than 10 to the 6 solar mass, stellar mass. Also, half-light radius and half, maybe it can be directly compared to half mass radius are estimated, and those quantities well agree with the observed quantity from Van et al. 2018 and Ma et al. 2020. However, in low metallicity run, you can see that less star clusters are produced. So yeah, this should be our future work. So we need to start from initial conditions based on the newly done deep observation of NGC 1052 DF2 and nearby galaxies. So yeah, so these are our parameter studies. So you can see that if we increase stellar feedback energy, less stars are produced and less star clusters are produced. And so this is comparison of fiducial and low metallicity run. So you can see that in low metallicity run, less stars and star clusters are produced, though still there exists dark matter deficient galaxy. So thank you for listening, and this is my summary of talk.
Thank you very much. So we have time for questions. Please feel free to raise your hand or just post it on Slack, and I'll try to read it out loud. Let's see, I don't see raised hand, but maybe people are typing, so we can wait a bit. Rohan Naidu has a question.
Yeah, this is a great talk. Thank you so much. What do you estimate is the probability of such collisions happening among like field galaxies and cluster galaxies and such? And do the observed like frequencies of these UDGs match up with what do you expect the frequency of such collisions to be?
Oh yeah, so yeah, that's a very good question, and we tried to look at cosmological simulations like illustrious TNG, and then we could find some pairs of dwarf galaxies that match our criterion of these this initial condition. So like this, so we could filter out some collision configuration in those simulations and got some number, but I think it's very rare. And in illustrious TNG, we did not see the remnant of the collision. I mean, dark matter diffusion galaxy produced after the collision. So yeah, I think this event is very rare, and I heard that Professor Peter van Dokkum wants to constrain the statistical probability of this event, like by observing, something like NGC 1050 to DF2. But yeah, it's very hard to do that, and we hope it can be like achieved in the future. And also, we should run more cosmologically plausible initial condition, and then you can maybe constrain the probability that you can find these pairs in maybe early proto clusters or something? Yeah.
Good. Thank you. That was comprehensive.
Thank you very much. So again, if there are more questions, please post them on Slack. And I think we can move on with Lise Ramambason from CA, whenever you're ready.
All right. So my name is Lise Ramambason. I'm a final year PhD student at CEA in France. And thank you very much for giving me this opportunity to present my work. Today, I will be talking about the escape fractions that we estimate from emission lines in the Dwarf Galaxy Survey. So the Dwarf Galaxy Survey is a survey of local low metallicity galaxies with a lot of peculiar properties, including very low masses, compactness, and especially subsolar metallicities. Which is reminiscent of the conditions that we expect to find in higher redshift galaxies. And I will point you to Susan Madden's talk for more detail on this sample later this afternoon. In this study, we will focus on only the unresolved galaxy within this sample, for which we have both Herschel and Spitzer spectroscopy. And this is a selection from Cormier 2019, for which we have a full spatial coverage of the core of the galaxies. And the data that I will be using in my analysis are only integrated spectrum over the whole aperture of the spectrograph. So just as an illustration, this is one of the galaxies in our sample, NGC 1705, seen this time in optical, where we have a very nice spatial resolution, and you can nicely distinguish the different phases of the ISM, especially the different level of ionization, which are traced here by sulfur 3 and sulfur 2 lines. But this is the view that we have when we look in the infrared, and this is the kind of data that I will be using. And as you can see, all the emission from the different phases of the ISM is then completely blending into one single beam. And this is really the problematic that was driving our modeling approach, because we cannot actually constrain a model of the ISM where you distinguish several regions or several clouds. And we decided to use instead topological models, which is representative view, combining different sectors to represent the complexity of the ISM. And I advise you to look at Vianney Lebouteiller's talk later today to know a little bit more on the different modeling approach that we have. With that kind of topology, there's some questions that we can now tackle, including quantifying the molecular gas in a galaxy, or quantifying the mass of dust, but also looking at the fraction of line of sight which is covered by neutral gas, known as a PDR covering factor, looking at the effect of compact object on the surrounding gas. And finally, the question that I will be talking in today is quantifying how porous the galaxy to ionizing photon, and more specifically, inferring the fraction of Lyman continuum photons that escape from H2 regions. Now, we have already seen during the past 2 days that several observational proxies are available to study the Lyman continuum escape fractions. The first one being direct detection in the UV, and we have seen that there have been a growing number of detection, including very recent ones that were presented in Sofia Flori and Alberto Saldaña-Lopez talks. But we can also use indirect tracers when no direct detection is available. And the first method is looking at line kinematics, Lyman alpha or magnesium 2, or looking at absorption lines. And in our case, I will be presenting a method which is based on looking at integrated emission lines. And this method has two great advantages. The first one being that it's almost independent of line of sight variation, and also that it is possible to apply it at high redshift. But to do so, we need to have a complex enough topology to represent the ISM. So these are previous results that were obtained with a topology-based approach. The first one being that in the DGS sample, we need to account for density-bounded sectors in order to reproduce the emission lines that are observed. And the second one concerns the PDR covering factor, which was studied in detail in Cormier 2019, and where they found that the PDR covering factor, which are derived, are always below unity, and that they are dependent on the metallicity of the galaxies and also of the spatial scales which are observed. And finally, in another sample of galaxy, which are non-leaking galaxies, we propose to use a combination of both density-bounded and radiation-bounded sectors in order to match the emission lines that were observed. And the approach that I will now describe is based on a similar idea, but on a more automated way to combine different sectors. And this time we are trying to quantitatively infer the fraction of photons that manage to escape outside of the H2 regions. So to do so, we developed a new Bayesian code, which is called multigris, and which relies on the Monte Carlo sampling to derive as outputs the posterior probability density functions for different parameters. So the PDFs that we are interested in are either for the primary parameters in our grid or for secondary parameters, including the escape fraction, or also for lines, whether detected or undetected. And here on the right-hand side of the plot, I show you the formula that we use to derive the escape fraction, which quantifies the number of photons produced by the central cluster, which are not absorbed within the different sectors. And by doing so, we were able to reinterpret some previous results from Cormier 2019, which showed that the PDR covering factor evolved as a function of metallicity, and that galaxies with a higher metallicity were less porous to ionizing photons. And this is also what we find, but this time by inferring the escape fraction itself, and we see that it decreases as metallicity increases. And this can be linked to the absorption of Lyman continuum photon, either by neutral gas, but also maybe by dust, because the galaxy with higher metallicities are also the one in which we have the highest dust to gas mass ratios. And it can also fit in the picture of recent simulations from CLIM 2019 and U 2020, showing that at higher metallicity, the burst clouds in which the star form are dispersed in longer time scales, and that the stars stay enshrouded for much longer times at high metallicities. However, when we convert this escape fraction and we plot it for the individual object, we see that we get very high escape fractions, which are consistent with what is observed in result observation, but are difficult to link to global measurements for the whole galaxy. And maybe one reason for that is that we may miss one diffuse component surrounding this H2 region representation, or that our configuration are still not complex enough. We also see that we have very large scatters, which led us to examine other dependencies in other parameters. And here I show you the dependencies on the stellar age, the stellar mass, and the specific star formation rate. And as you can see, we find that one of the best correlation of this H2 region escape fraction is with the specific star formation rate, which fits the picture of the feedback-dominated process, and which is also a trend which was presented in Sophia Fleury's talk from Monday with the observed global escape fraction of Lyman continuum. And finally, the last thing that we can do is to try to find tracers of this escape fraction. And here I present you two line ratios, O3/C2 and O4/C2. The first one has the great advantages of combining two very bright lines, which are detecting in most local galaxies, and which are also detected for high-redshift galaxies with observatories like ALMA. And the second one has the great advantages of having a greater dynamical range, although the detection of O4 is more challenging, but it should be possible for more and more galaxies with the upcoming JWST. And I leave you with my key messages, which are that with multigris, we can recover topology, even from spatially unresolved observation, and that we have used it to derive the predicted escape fraction from H2 regions. And we find that it correlates with both stellar age and specific star formation rate, and anti-correlate with metallicity. We also identified some line ratios which could be used as tracer of this H2 region escape fraction. And we hope that this method could be applied even for high redshift galaxies with the new detection coming with ALMA and JWST. And with that, I thank you for your attention, and I will take questions.
Thank you. Thank you very much. Perfectly on time. I think Andrea Ferrara has a question.
Yeah, thank you very much. I enjoy your talk. And just a quick question on the on your interpretation of the positive correlation between escape fraction and stellar age. How do you interpret that?
Well, so in our case, in this model, we are only combining sectors around one single star population, which is a burst with a given age. So the age that we derive here may not be representative of like all the stars in the galaxy, but only of the dominant population. So one way to see to interpret this would be also based on the simulations from Yu et al. That I presented, which who saw that that the escape fraction, like that it takes a minimum time for the stars to break outside of their host cloud, and hence a very young population could not produce high escape fraction because they are still very enshrouded in the clouds. However, with our hypothesis of a single age, we also might have a dependency of the stellar age and metallicity, like maybe a degeneracy. And so since the metallicity is driving our escape fraction, it might be that the higher age are associated to high escape fraction because they correspond to the lowest metallicity galaxies also.
I see. Okay, thank you very much.
Great, there is time still for one question, if anyone has. Alberto Saldana.
Yes, thank you, Lise, for this lovely presentation. I have the same question than yesterday for Choi talk. So is your H2 escape fraction is at the end, it's an integrated escape fraction over all wavelengths, right? It's not monochromatic as we measure the when we detect direct alignment continuum detection, we usually measure the escape fraction at 900 Armstrongs or so. So this escape fraction is integrated. Is that right?
Yeah, exactly. It's a very good point. But here we are considering the integrated photon above 1 Rydberg. So it's not monochromatic. It cannot be compared directly to observation. But I think there are also other hypotheses in our model that prevent a direct comparison. But it's a very good point. Yes.
Yeah, that's maybe why you are obtaining sometimes such a high escapes. But yeah, it's a very, very nice code.
Thank you.
Great. Thanks, Lise, again. And I think we can move to the last talk of this session by Hiroya Umeda from the University of Tokyo.
Hello, can you see my screen?
Yep.
Okay. Hello, I'm Hiroya Umeda, a first-year graduate student at the University of Tokyo. Today, I will present my research on the ionizing spectrum shapes of extremely metal-poor galaxies. And these are the collaborators of my research. So, There has been a long debate on the origin of strong helium-2 emission lines from extremely metal-poor galaxies. And the picture on the left shows the strong helium-2 emission line relative to H-beta emission line in one of the EMPG. And there have been difficulties reproducing this strong helium-2 emission line. This is illustrated in the figure on the left, on the right, I mean. And x-axis is ionization parameter, and y-axis is helium-2 H-beta ratio. And the stellar population model called B-bus binary model, which incorporates hard ionizing photons from binary stars, can only explain up to 1/3 of the observed helium-2 H-beta. And this suggests that extra ionizing sources are needed. There are lots of excellent works published recently to solve this problem. For example, Olivier et al. Added blackbody to increase hard ionizing photons production. Lebouteiller et al. And Simons et al. Added ultra-luminous X-ray sources. And Ezotov et al. Claimed that the radiative shocks in non-uniform ISM might explain the strong helium-2. However, there remains a problem. For instance, if you look at Olivier et al. Results, x-axis is ionization parameter and y-axis is the flux of O3 and helium-2 relative to H-beta. And you can see that their best fit model shown in the dashed line does not explain observed O3 line together with helium-2 simultaneously. So these mismatches raises a question that whether a self-consistent simple model exists. So we take a new approach to tackle this problem. We use information of emission line fluxes to determine the general spectrum shape of ionizing spectrum, especially around the ionization energy of various ions. We illustrate our general spectrum in red, and x-axis is wavelengths and y-axis is flux, and dark and dashed line represents the ionization energy of several ions, including helium-2. To determine general spectrum shape, we construct ionizing spectrum model from a black body and power law radiation. Then we validate black body temperature, power law slope, and mixing ratio between these two components to determine the general spectrum shapes that can explain all the major emission lines simultaneously. Let me first explain our sample. Our sample is composed of 3 galaxies. Their metallicities are all below 10% solar. And J1631 is the most metal-poor galaxy with metallicity 1.6% solar. J104457 is one of the EMPG studied in Olivier et al. And last 1318 is one of the most well-known and studied EMPGs. For these galaxies, we investigate their general spectral shape. Next, we will explain emission lines used to determine the general spectrum shapes. First, we use hydrogen lines, then the oxygen 2 doublets, helium-1 lines, oral and nebula O3 lines, and helium-2 line, and then sulfur doublets. Before sulfur doublet, we take ratio between the doublet to minimize the uncertainty from abundance ratio. So we basically utilized about 10 major emission lines, carefully avoiding uncertainty of abundance ratio. Next, let me explain our photonization model. First, we specify ionizing sources. Then we calculate radiative transfer in H2 region using photonization called cloudy. Then we compare the projected emission line fluxes from cloudy calculation to the observed emission line fluxes. We use the ionizing spectrum we described before with three parameters for the spectrum shapes. Then we also vary ionization parameter. So we also vary ionization parameters, gas density, gas metallicity, and H-beta flux. And so we explored for the self-consistent model by varying a total of 7 parameters in the range shown in the table. Then we combine our photonization model with Markov chain Monte Carlo MCMC technique to determine the self-consistent model that explain all the emission line fluxes simultaneously. The figure on the bottom shows the convergence of the parameter during the MCMC fitting, and the figure on the left shows the result of MCMC. The top panels represents the histogram for each parameters, and other panels shows distribution of sampled parameter sets. Red line shows the location of best fit parameters, and dashed lines represents the uncertainty range defined by likelihood value. You can see that the parameter sets with high likelihood value, represented in orange dots, are concentrated around the best fit parameters, suggesting a good convergence. So let's take a look at the emission lines. First, for the J1631, the x-axis is wavelengths and y-axis is x-axis is wavelengths for emission lines, and y-axis is a difference between model flux and observed flux, normalized by observed flux. And red and yellow bars are 1 sigma and 3 sigma range for observed flux, respectively. The black dots represents the flux reproduced from the best fit parameters, and we can see that for all the emission lines are within around 3 sigma error. And for J104457, also all the emission lines are reproduced within around 3 sigma errors again. And also for 1-18, again, all the emission lines are reproduced within 3 sigma, around 3 sigma. So yeah. And next, let us present the general spectrum shapes reproduced from the best fit model. The x-axis is wavelengths and y-axis is flux. Red, orange, and blue lines are the general spectrum shape for our 3 galaxies, and dots and bars represent the flux values and its uncertainty at each ionization energy for the ions of emission lines. Blue faint line, the gray faint line is a spectrum of B-pass binary model at 10 megayears, and black cross represents its flux at each ionization energy. And then let's compare our result with Olivier 2021's result. For J104457, left panel shows the best fit spectrum presented in Olivier 2021 in green color, and the mock model shown in the dark blue. The right panel shows the results for the mock model for Olivier 2021, and you can see that the lack of helium-2 H beta is resolved by their model. Next, we overplot our result in the red color. Our spectrum has different spectrum shape compared with Olivier 2021, and you can see our model also explains helium-2 H beta, but this time together with other lines, including all 3 lines. Let's go back to our result. You can see that the black body-like shape, you can see black body-like shape for J104457, while you see concave downward shape for J1631. And I3K18. And also for these 2 galaxies, you can see parallel components. These 2 types of spectrum shape suggest the diversity in the spectrum shapes of ionizing spectra in EMPGs. Lastly, we will briefly discuss about the origin of ionizing spectrum. First, let's compare the stellar model. As you can see on the left figure, the spectrum of B-pass binary model are completely different from J1631 and 1-18, as the B-pass binary cannot reproduce such a parallel component and concave downward shape. And also, even for J104457, it needs parallel to explain ionizing fluxes around helium-2 ionization energy. So this suggests that they need non-stellar sources. Next, we considered the combination of BBUS single star model with ULX model. We first overplotted only single star model on our best fit model for J104457. Then we add ULX to the single star model. And now we can see that this single star model with ULX model can explain the spectrum shape for J104457. And spectrum shape for J1631 can also be explained by ULX and single star model, as shown in the red. And when we compare both spectrum, you can see that the diversity in spectrum shape can be attributed to the difference in stellar contribution. Also, when we look at the stellar ages inferred from the stellar components, J104457 is very young with age only 2 megayears, and J1631 is a bit older with 6 megayears. This suggests that the diversity in the spectrum shapes can be explained by how stellar components are less prominent for the age older than about 5 megayears. And this is my summary, and thank you for listening.
Thank you very much.
Thank you.
So we're open for questions. Vianney Lebouteiller.
Hi, can you hear me?
Yes.
Thanks a lot for the talk. It was really interesting, and I think it's really the way to go to constrain these radiation field shapes that we really don't know much about, and there are no easy way to do it directly. I was just wondering whether you have investigated maybe the higher ionization lines like neon 5, even if there are upper limits, because even the upper limits might bring useful constraints for such an inference of the spectral shape.
So you mean that did we test the more higher ionization lines such as neon 5? And
yes.
Okay. Yeah, I mean, in our study, we did not check that, but sure, it's to avoid abundance, uncertainty of abundance ratio, but yeah, like in future, and we can check that easily. So yeah, I'm happy to check that. Yeah, thank you. Thank you for a nice comment.
Nice. So we still have time for a question, if someone has. So there is one in Slack. So Ryan Vogt is asking, any thoughts on a physical origin for IZW18? Does single plus ULX not produce the general shape of the ionizing spectrum?
Sorry, I couldn't understand the first part of the question. Can you repeat the question?
So I can read it again, and then if Ryan would like to clarify, then you're encouraged to unmute yourself and maybe comment on this. So any thoughts on a physical origin for IZW18? Does single plus ULX not produce the general shape of the ionizing spectrum?
Not producing the general spectrum. Yeah, the physical origin of the ULX okay, I got it. Yeah, I actually tested for 1Q18 also, and I didn't post it right here, but for 1Q18 also showed that we were able to reproduce the general spectrum shape of BBUS of 1Q18 using BBUS single and ULX, and it had similar shape as J1631 with stellar age older than 5 megayears. Yeah, thank you for a nice question.
Nice, and there is a last one by Ayush Saxena. Very nice talk. Do your ULX-driven X-ray luminosity predictions also match up with observations for these sources?
Thank you. And yeah, I actually checked the X-ray luminosity to star formation rate ratio, and I found out that for all 3 galaxies, the value was comparable to the observation of metal-pole galaxies value. Yeah.
Great. So many thanks to Hiroya and to all the speakers of this session. Thank you. I would like to ask all the participants to please stay a bit longer in this plenary room. I think Yuki would like to take a picture, a conference picture. So maybe, I guess, we can turn on the cameras and I leave Yuki to coordinate this.
Mm-hmm. Yeah, thank you for your explanation. Yeah, please turn on your camera. That's ready. And yeah, great. I will take 4 photos. So please smile every time. Okay, I will take a first picture. So 3, 2, 1, smile. Yeah, okay, great. And next one. Okay, 3, 2, okay. Then 3, 2, 1, smile. Okay, next. All right. Okay. Okay. 3, 2, 1, smile. Great. And the last one. 3, okay. 3, 2, 1, smile. All right, excellent. Thank you for your cooperation.
Thanks. So I guess at this time you can join the breakout rooms if you would like to discuss more with the speakers. And otherwise, feel free to take a break. And I think we can rejoin at, well, in 20 minutes for the next session. Thank you all.
Our speaker for the next session, hello everyone. So if you would like to do a test screen sharing, now it's a good time
to try myself.
Yeah.
Does it work?
Yes, it works perfectly. Vianney, would you please let me know how you should pronounce your last name?
Oh, the last name is complicated, but it's Lebouteiller. It's okay. You can just say Vianney or Vianney. It's fine. Don't worry.
I'll try to pronounce it correctly.
Thanks.
Hi, and can I try sharing my screen, please?
Yes, sure.
I'm in the, I think I'm the second talk after the break. And my
Yes.
name's not complicated, like Vianney's.
Suzanne Madden. Yes, please go ahead.
Okay. So,
Perfect. Yes.
you don't have to read my titles. I couldn't choose, so I have lots of titles.
Sure. Do you wanna? Yes, perfect. Okay, I can see the slides.
Thanks.
Thank you. Matilde, do you want
yes,
to?
I will share my screen. Can you see my slides?
Yes. Perfect. Yep. Thank you. All right, let's see.
And can I share my screen? My name is Luwenjia Zhou. And the third speaker, I think.
Yes. Please go ahead. Share your screen.
Share my screen. Right.
Oh, did we? I think we lost her. Let's see. Who else is in the session? Mahtab Gholami. Would you like to screen share?
Hello, thank you. Yes, I tried to do that. Could you see it?
I can see it, but it's not in full screen mode. Yeah, if you go to slideshow, there should be an option.
Oh, okay. Oh, it is on the slideshow, but
oh, I see.
Could you do that?
No, it's still not on full screen.
I think it's because you're sharing the second screen, maybe, or the full screen. You can choose to share the application or the screen where there is the talk projected.
Is it okay?
Yeah, when you do screen share, when you share a screen from Zoom, maybe instead of sharing the maybe share the application, or whatever you're doing, do the other way. If you're sharing the application, share your whole screen. If you're sharing your screen, share the application. I think that will solve it.
Yes.
So stop this screen sharing and do it again.
Oh, okay. Is it okay right now?
No, still it's not in full screen mode.
Oh.
So when you share a screen, are you sharing your app, the application or your whole screen?
No, it's just web browser.
Okay.
And what about it? It's not okay right now?
No, it's still showing your whole the whole app. It's not only on the slide. You can see the
Oh. It's not okay?
nope. Still Matilde, can we try with Luwenjia first, because she's before you, to make sure her screen sharing is working okay while you're figuring it out?
Yes, okay.
Yes, I'm sorry, I forgot to authorize Zoom for the screen sharing, so I had to relaunch Zoom. I will try to share my screen again.
Yes, please.
You see my screen?
Yes.
And
the slides is perfect. Can you move forward to one slide maybe? Yeah, great. Thank you.
Perfect. Thank you.
Okay, now let's go back to Matilde, figure that out. So Matilde, maybe
yes.
When you're sharing, you said it's on a browser.
Okay.
What application are you using for? Okay, perfect. Okay, now try it again.
Is it okay?
Let's see. Yes, now it's okay. Can you move forward? Yeah, perfect.
Okay, thank you so much.
Sure.
Hi, Irene. I'm Yuki, the behalf of LLC.
Hi, Yuki. Yeah.
Hi. Yeah, nice to meet you. Do you see the presentation clock I showed?
It was somewhere. Now I lost it, but yes, yes, I can see it. Yeah.
Yeah, I count the time. Yeah, so please use it.
Yes. So for all the speakers, as you know, the talks are 10 minutes plus 5-minute question.
Yes.
Please try to be on time.
Yeah, it's totally up to you whether you remind the time.
So for reminding, is reminding by chat the best way, or
on the first day, Masami speak out at the 10-minute.
Okay.
Yeah, maybe that's enough.
Okay. If you're over time by more than 1 minute, I will speak up. But yeah, please just try to be on time.
Yeah, thanks so much.
Thank you, Yuki. Okay, we'll start in a few minutes.
Yeah, I will close the breakout room now.
Hello, everyone. Thanks for coming to the last session of today. So we are at the past half an hour. And our first speaker for this session is Matilde Mingozzi from SCSCI, talking about UV ISM diagnostics in local high-redshift analogs with Classy. Matilde, please take over.
Thank you, Irene. I will share my screen. Can you see it?
Yes, perfect.
So, hi to everybody. I'm Matilde Mingozzi, a postdoc at Space Telescope Science Institute. And I'm working in collaboration with Beth and James and the other people that you see here. And today I want to talk about UV interstellar medium diagnostics in local high-redshift analogs with the Classy survey. Before starting, I want to thank the organizers for giving me the opportunity of presenting my work today. So UV spectra, they provide a unique window on many important diagnostic features because they can give us information about massive stellar population, chemical evolution, feedback processes, and the ISM properties. And so this is an example of a rest frame UV spectra from the Lyman alpha feature to that can be damped or in emission, the ISM absorption features, and other nebular emission lines. And these lines are observable in the local universe with the rest frame UV spectra with HST, and then moving towards the high-redshift universe, they can be visible in the rest frame optical and near infrared. And with JWST, we will have rest frame UV spectra at redshift higher than 6. So we will be able to see UV spectra for the main characters of the reionization. And so it's important to understand very well the UV diagnostics and what they can tell us in the local universe, where we can observe them with much more detail and in order to have a toolkit to understand better high redshift systems in the nearby future. So this is one of the aim of the Classy survey. Classy is a cost legacy archive spectroscopic survey of 45 local star-forming galaxies. And the peculiarity, so these star-forming galaxies were selected to be highly representative of the high-redshift universe in terms of different properties. For instance, the stellar mass goes down to 10 to the 6 solar masses. We have very low gas phase metallicities, high star formation rate, high specific star formation rate, and also our targets are characterized by high O3 O2 line ratio, that is a measure of the ionization parameter, and so the ionizing photons. Moreover, the important peculiarity of Classy is that it collects together 3 gratings from the COS instrument on HST, so the G130M, the G160M, and the G185M. So basically providing spectra that goes from the Lyman alpha till the carbon-3 lines at 1900 angstrom. Providing the first high-quality, high-resolution far UV spectral database of nearby star-forming galaxies in a so broad wavelength range. And in particular also, since the COS aperture is of 2.5 arc seconds, and since our targets are, for the majority, are compact, similarly to high-redshift systems, the COS aperture can cover very well the majority or all of the emission. My work, as my current work on Classy, has been focused on the study of the UV emission lines. Here are underlined some of the emission lines that I am looking at, and in particular, I want to show you some examples, since we observe carbon-3 emission lines for 33 out of 45 galaxies of our sample. And here you see on the right, you can see some examples. So In many targets, we can see the two lines clearly blended, while in some cases we have blended features. We see in 28 galaxies out of 45 helium-2 and oxygen-3 emission lines, and in 10 of them, we also observe the carbon-4 lines in emission. And this is interesting because carbon-4 is a resonant line, so the fact that we see it in pure emission is currently under investigation. Furthermore, for our targets, apart from the COS UV spectra, we also have optical spectra that we collected from different instruments from SDSS, LBT, KSWI, and MUSE. And this is allowing us to do a UV optical diagnostic comparison. If you go and look at the poster of Carla Arellano, you will see a detailed comparison of the optical properties for the different apertures, for the different dataset that we have. So going to the comparison between the UV and the optical diagnostics, I will start with the density. So first of all, I want to remind you that star-forming regions are stratified, and they are characterized by different species that have different ionization potential and different critical density. So for example, the lower ionization potential, you will find, for example, talking about the density diagnostics, the sulfur 2 lines in the optical. Then going towards higher ionization potential, you will have DO2, iron 3, and then in the optical, in the intermediate, if you divide the star-forming region in 3 different ionization regions, so a low, an intermediate, and a high ionization region, in the intermediate you will have the chlorine 3, that is a good density diagnostic. In the UV instead we have the silicon 3 or the carbon 3 emission lines, and going towards high ionization potential you have the argon 4 or the nitrogen 4. So I calculated the densities using all these different diagnostics to see how the UV ones compared with the optical ones. In particular, the most used optical diagnostics is the sulfur 2. That you can see here, the sulfur 2 line ratio as a function of the density, how it varies as a function of the density, while these 3 diagrams on the right shows the UV density diagnostics, so the silicon 3, carbon 3, and nitrogen 4 line ratios. Already from here you can see that while the sulfur 2 densities are more or less around 10 to the 2 centimeters to the minus 3, the UV diagnostics are all shifted towards higher densities, since these species are characterized by higher critical densities. But you can appreciate better the result in this plot over here. I will drive you through this plot. So in this plot on the y-axis, there is the density of the interstellar medium, while on the x-axis, you have all the 45 classic galaxies ordered at increasing stellar mass. And the main panel shows the values of the density that we obtained using the sulfur 2 lines in the optical, and these are the magenta squares, while the other markers that you see are the densities that you get from the UV. So in particular, the yellow triangles are the carbon 3 densities. And if you look at the bottom panel shows the difference index between the generally used sulfur 2 densities and the other diagnostics. And you see that there is basically a median scatter, or a median shift of 2 decks between the two. We are investigating if this shift is varying as a function of galaxy properties or UV or other optical observables. And at the moment, this offset seems to be constant and fixed, not dependent on any galaxy properties. Talking instead about the temperatures, in the optical, we have different temperature diagnostics for the different ionization zone. One of the main used diagnostic for temperature is the ratio between the O3 auroral line and the O3 nebular line. And since in our spectra, we have in our COS spectra, we have the UV O3 line at 1666, we are testing if we can use this hybrid temperature diagnostic that is comparing the UV emission line with the nebular optical one. So in particular here in these two plots, you see on the left the optical O3 line ratio as a function of the temperature, and then you see the hybrid O3 line ratio as a function of the temperature. In particular, the hybrid O3 line ratio the relation seems to be slightly steeper, and so without bending at higher temperature, and so it could be a better tracer than the optical one. We measured the temperature with the two different O3 ratios, and you can see the optical O3 temperature in blue, while in cyan you can see the hybrid O3 temperature. In overall, the hybrid O3 temperature is slightly higher with respect to the optical one, and you can see that in this bottom panel here, you see that more or less the points are slightly. The points that represent the difference index between the optical temperature and the hybrid O3 temperature is slightly lower than 0, meaning that the hybrid O3 temperature is slightly higher. Unfortunately, we find that this difference is correlating a bit with the gas metallicity. And in fact, if you calculate the metallicity with the two temperatures and you do the difference between them, as shown in this plot on the right, you will see that this difference can go between plus and minus 0.2 dex and is correlating with the gas phase metallicity, which means that if you use the hybrid O3 temperature, you could underestimate the metallicity at low metallicity and overestimate the metallicity at high metallicity. We are currently investigating better this problem to understand how to use this hybrid O3 lane ratio. Apart from that, we are testing other temperature and so gas phase metallicity diagnostic using only UV information. And at the moment, we found promising correlation between the O3 helium-2 line ratio and the temperature and so the gas phase metallicity, and also between the carbon-3 equivalent width and the temperature and so the O3 metallicity. We are currently understanding if there are further dependence on these diagnostics, for example, on the ionization parameter. At the moment, the ionization parameter is calculated only from optical diagnostics, so from the optical O3 O2 line ratio that is the most used, and we are trying to see if there is a diagnostic in the UV that we can use to measure this parameter. The only thing that we tested at the moment is the carbon-4, carbon-3 line ratio. That is not visible. The carbon-4, unfortunately, is not visible in many targets, so we have just 8 points here. But at the moment, if the carbon-4, carbon-3 line ratio seems to well correlate with the ionization parameter in the optical. So this could be a useful proxy for ionization parameter in high-redshift systems, where carbon-4 line could be more easily visible. So I am a little bit over time, so I will leave you here with my conclusion. I just want to stress that with GLASSY, we will be able to provide a complete set of UV diagnostics to investigate high-redshift systems when you will have only the UV available to study their properties. Also we are also trying to find diagnostics, trying to test diagnostics to study the different sources of ionizations. And since we have integral field spectroscopy data available for our GLASSY targets, we are also comparing them with our UV spectra. And in the nearby future, we will have also for 3 of our targets imaging of UV emission lines, such as Lyman alpha, carbon-4, carbon-3, carbon-3. So we will be able to study also the distribution of these emission in our systems. So sorry for being a little bit too long, and thank you for listening.
Thank you, Matilde, for a very nice talk. If there are any, if there is a quick question right now, I don't see any hands. There is one question in the Slack. I'm going to read it. So can you comment on how much the local variation of ISM condition for each galaxy contribute to the variation of T and N temperature and electron density over different galaxies? Does your spectrum cover a similar spatial scale for each galaxy?
Well, later I will also read read more in detail the question, but so this is what we are trying to do. So to see how our diagnostics are in the UV are varying with respect to the optical according to the different properties of the galaxies concerning. So concerning the densities, for example, we are trying to see if the UV densities that you get are how they compare to the optical and how they vary with the galaxy properties. So for the UV, we find that in general, the UV densities are higher of 2x with respect to the optical densities. And this variation seems to be independent on galaxy properties because it's constant and fixed for all galaxy properties in terms of density. In terms of temperature, instead, we find this slight dependence of the variation of the temperature that you can get from the hybrid O3 diagnostic with the gas phase metallicities. So yes, we will investigate how the properties vary with the. We will investigate this in detail, and our work will be available between the end of this year and the beginning of next year with the results.
Thank you, Matilde. Unfortunately, we're out of time, but I encourage you to write your questions in Slack, and there is already another one, Matilde. So let's move on to our next speaker, Susan Madden from CEA. She will be talking about the ISM properties of local universe low metallicity dwarf galaxies. Multiple titles. Thanks, Susan.
Yeah, I know I have too many titles here. I couldn't decide on which one. So, but in principle, I'd like to highlight a few characteristics of our local universe star-forming dwarf galaxies and these characteristics that have emerged from our observations and discuss what this is telling us about their structure and their ISM. And these analyses focus on the mid-infrared and far-infrared observations from the Dwarf Galaxy Survey, already introduced by Lise a couple of talks ago. This work has been ongoing over the last few years in our group at Saclay, and this presentation will draw from a few recent papers. I'll highlight a few of the extreme observational signatures we see in these local universe dwarfs and how they're observationally different from more metal-rich galaxies, and also where they may resemble some characteristics of high-redshift galaxies. So star formation surface density correlates with molecular gas surface density in normal metal-rich galaxies, such as spirals and starburst, local starburst galaxies, describing how efficiently gas is converted into stars, as in this Koenig-Schmidt relationship. But for low metallicity star-forming dwarf galaxies that we've been looking at, the molecular gas traced by CO is weak or undetected, as shown here in the red stars. And why is this? We could ask, is star formation proceeding differently in these dwarf galaxies? Or is this due to very efficient star formation from little molecular gas? Or is CO not tracing the full molecular gas reservoir? Here then is the enigma that we're faced with. It's very difficult to detect molecular gas, the fuel we need for star formation in these dwarf galaxies undergoing vigorous star formation. And this really is important to understand if we want to understand the conditions for star formation in the early galactic environments. And in the following talk, Luwenjia will actually present some of the findings of the deepest, maybe marginal detection of CO in 150 18, one of our lowest metallicity local universe dwarfs. So that's really interesting. So another outstanding signature we see in the dwarf galaxies, here we see the global, these are all global observations I'm showing to you, integrated over the full galaxy. The global C+ and the CO normalized by their far infrared luminosity for a wide range of galaxies. They're shown here. And we show lines of constant C+ to CO ratios, while most normal and starburst galaxies have C+ to CO ratios between 1,000 and 4,000 in this area here. For the dwarf galaxies shown in red, these are higher ratios, up to an order of magnitude higher C+ to CO than we observe in the dustier starburst galaxies, for example. So what's this high ratio of C+ to CO telling us about the dwarf galaxies, their ISM and their star formation properties? Another of the outstanding observations we see that I pick out is the far infrared 88 micron line, which was observed in our Dwarf Galaxy Survey to be very bright. And note here that it requires 35 eV to reach this ionization state, whereas C+ is only 11.3. And here we show the O3 to total infrared luminosity versus the total infrared luminosity. The dwarf galaxies are these colored symbols, and the more metal-rich galaxies are these red points. And we find up to even about 1% of the far infrared luminosity comes out in the O3 line. And on the right here, we show the O3 to C+ ratio. And what we see, we know that in more metal-rich galaxies, C+ is really the brightest line in the far infrared. But in the dwarf galaxies, the 88 micron O3 line in the far infrared is brighter than C+. It's the most luminous far infrared line. So it looks like the low dust abundance in dwarf galaxies encourages the propagation of the hard UV photons, resulting in the overall luminous O3 line throughout the galaxies. And so dwarf galaxies also show high ratios of other lines involving high ionization potentials, like a high neon 3 to neon 2 ratio, a high sulfur 4 to sulfur 3 ratio. And so what it looks like, it's suggesting a change in the ISM porosity from the Dutch rich galaxies down here to the dust poor galaxies, which may facilitate the escape of ionizing photons in some systems. In the dustier galaxies, of course, the hard photons are absorbed close to their ionizing source, where the low metallicity galaxies have very large filling factors of ionized gas. So, so it looks like the ISM structure at low metallicity is very porous, clumpy, lots of diffuse ionized gas. And in Lise's talk earlier, she quantifies the actual photon escape fractions in our dwarf galaxies using her multi-phase model. And she takes all this work that we start to the next step and uses a more complex multi-sector combined ISM model with a Bayesian approach to actually quantify the escaping photons. And so the O3 to C+ ratio is also observed to be very high in high redshift galaxies, similarly to those ratios that we see in the local universe dwarf galaxies. For example, in this Harakane et al. Study of redshift 6 to 9 galaxies, these ratios, the O3 to C+ ratios, can be as high as 10 or even more. And our local dwarf galaxies have always we always see a ratio of between 1 and 10, so similarly high. And Livia Vellini's simulations also find high O3 to C+ ratios in epoch of reionization galaxies. And so in the O3 to C+ ratios that we see, our dwarf galaxies seem to resemble these epoch of reionization galaxies. So in our Dwarf Galaxy Survey, many of the compact local dwarf galaxies in the local universe are observed with Herschel and Spitzer and are unresolved in the far infrared. However, with so many mid-infrared and far infrared fine structure lines of widely varying critical densities and energies, we should be able to uncover properties of the different phases, the the lower and high density phases and the neutral PDR phases. So with Dion Cormier, we first modeled the dwarf galaxies applying the cloudy grid, self-consistently constraining the ionized phases and PDR regions in these first multi-phase models. And for this presentation, I choose to look into particularly the molecular gas reservoir from the models. So what we do is we extract the total H2 from the models, and the models which well constrain all these observations. And then we compare the total molecular hydrogen mass from the models with the molecular gas that's traced by the CO alone. And we quantify the molecular gas that's sitting outside the CO emitting region. This is the CO dark gas. And so what we find is in the y-axis in the left plot is the total molecular hydrogen from the model divided by the molecular hydrogen that's only associated with the CO emitting region. And effectively, it's the fraction of the CO dark gas. And the observed C plus to CO is on the x-axis. And we see that as the C plus to CO ratio increases, the CO dark gas is dominating the molecular gas budget. The molecular gas in the CO emitting region is not doing much. It's very, very small volume. And on the right plot, we can go from the observed C plus to the total molecular hydrogen, and this is from the models, and we derive a C plus to MH2 relationship. And there are other studies developing C plus to trace H2, and I point out Anita's recent results also using the dwarf galaxies also with their high redshift galaxies. So taking into account now the dark reservoir of molecular gas brings our dwarf galaxies that were outside the Kinnick-Schmidt relationship back onto the Kinnick-Schmidt relationship, because there's lots more molecular gas here. And when we use the molecular gas based on the C plus observations. And also from this, we find a new CO to H2 conversion factor as a function of metallicity. And our new value is this red dashed line, and these are our observed dwarf galaxies. And it's a lot steeper than some of these others in the literatures. But just to note that we haven't pinned down some of the really low metallicity galaxies, which require more sensitivity and are higher spatial resolution too. So in summary, just a couple of takeaway points. The dwarf galaxies, with their combination of high UV field and low dust abundance, have profound effects on what we observe compared to dustier star-bursting galaxies. Little CO, but vigorous star formation. And some of these ratios are quite extreme. They stand out in these high ratios involving especially high ionization potential lines. And the observations, some of these start to resemble high redshift galaxies toward the epoch of reionization. The consequences are that we don't trace the bulk of the molecular gas with the CO only in low metallicity environments. And we can do that with C plus. And the ISM structure is very porous and clumpy, very small filling factor of PDR that's been completely very photodissociated away. And so these are useful analogs probably to help interpret high redshift, low metallicity galaxies. And following up from this, we were going to be looking at the C1 lines to trace molecular gas in dwarf galaxies, which is also useful and helpful for high redshift galaxies. And then zooming into the local group galaxies to actually study the phase structure to understand better the ionized to neutral to molecular phase structures on parsec scales. And thank you.
Thank you very much, Susan, for the very nice talk. we have time for one question. Feel free to raise your hand. Rohan Naidu.
Hi, Suzanne. Very nice talk. So my question was that you're positing that because these galaxies have very low metallicities, they might be good analogs to HeII sources, but they could also end up with low metallicities because of very inefficient star formation, right? So for example, in the LMC, we see very, it's not like a bursty galaxy that has, that is comparable, I would say, to these HeII sources, no? So do you also need extra selections like Yuri Izador was showing yesterday to select for compactness and like these extreme line ratios as well in order for them to be faithful analogs? Or do you think metallicity itself is getting us most of the way?
So inefficient star formation, you mean, so how could they be very inefficient when they have such, I mean, I see these to be vigorously forming stars. They have relatively high, they have high specific star formation rate, and they are very compact, the ones we've been looking at. Yeah, so I don't know why they look like they're inefficient star forming galaxies. Maybe I didn't understand that.
I mean, just if you look at the star formation history of the LMC or the SMC that you showed on your first slide, right? Like they seem to have very extended star formation histories that have not always been fairly bursty and fairly high, right? They've gone through long periods of not very efficient star formation. But you mentioned that these are all compact and their SFRs are comparable. So I think that answers my question. Thank you.
I see. Yeah. So the local group galaxies are not in this particular study because we've been looking at the more relatively unresolved ones, but which is why we're now focusing on, we have some projects in the LMC in particular and IC10 and some of these local group galaxies that we can resolve better to understand, you know, what's going on the small scale. So we may find that when we look closely.
Got it. Thank you.
Thanks.
Thanks. It sounds also like a good discussion for one of the breakout rooms. So let's move on to our next speaker, Luwenjia Zhou from Nanjing University, talking about extremely weak CO emission in Zwicky 18.
Yes, thank you. Hello, I'm Luwenjia Zhou from Nanjing University. First, I would like to thank the organizers for giving me the opportunity to present my work on the extremely weak CO emission in IZW18, which is the galaxy I show here in this figure here. So IZW18 is one of the most metal-poor galaxies we've ever known. It has about a 3% solar metallicity, and it is also forming stars very actively, so that we expect to see molecular hydrogen to fuel this active star formation. So in this work, we use the NOEMA interferometry to observe the CO emission in IZW18. CO, as we know, has been used as the tracer of molecular gas in galaxies. But at low metallicity, it is difficult because first, CO is hard to form due to the lack of raw material at low metallicity. And second, as shown by this nice diagram in the work by Susan Maiden in 2020, the radiation field is harder in metal-poor galaxies, and the stellar light from the young and massive stars can penetrate deeper into the molecular clouds. While the molecular hydrogen, they can self-shield, the CO molecules, they cannot, and they can be dissolved easily into atomic or singly ionized carbon and oxygen. So in the observation, it is really hard to get CO observation detections at lower than 10% solar metallicity. So far, there is only one robust CO detection in sextans B. And in general, for the dwarf galaxies, which are mostly metal poor, the detection rate of CO is relatively low. So the CO conversion factor, the CO to molecular hydrogen conversion factor is actually very uncertain, especially at a low metallicity. So what we want to do is with IZW18 is to put a constraint at the low metallicity end in this plot. So here I show our NOEMA observation. We have got a 3.5 sigma signal in IZW18, which is shown by these red contours here. This is the peak of the emission, and we extracted the spectra from this region, which is shown here. This is the only 3.5 sigma signal we found in the entire observation, and it overlaps very well with the background, the stellar emission shown in the background V-band image. And we also show here with the yellow contours, the 1.3 millimeter continuum, which covers almost entirely the galaxy. So with the CO detection, we compared we show here the plot of star formation rate as a function of CO luminosity. So it has been found that the ratio between star formation rate and CO luminosity is higher in the metal poor galaxies compared to the normal star forming galaxies at solar metallicity. And IZW18 it actually shows an even higher ratio compared to the other galaxies. But what we are really interested in is the molecular clouds, the molecular component in this galaxy. So this ratio, star formation rate over CO luminosity, is actually the ratio between the CO conversion factor and gas depletion time. Gas depletion time is found to be close to constant in local spirals, which is also indicated by the well-known Kenta-Schmidt law. But still, people have found that the gas depletion time has an anti-correlation with the specific star formation rate, which is shown by the work of Santonge in 2017. And the IZW18 has a high specific star formation rate. And if it follows this also follows the trend, this will indicate that IZW18 has a rather low gas depletion time. Then the high ratio here and the low gas depletion time. With these two, we are still not sure about the alpha CO, whether it is high or normal. So this ratio is related to both metallicity and the star formation rate, because alpha CO is a function is influenced by metallicity, and the gas depletion time is related to a specific star formation rate. So in order to disentangle the effects, the two effects, recently the work from the magma survey by Hunt 2020, what they tried to do is that first, they found that there is a tight relation between this ratio and specific star formation rate for galaxies above solar metallicity. And they also found that the metal poor galaxies, they their ratio deviates from this tight relation, and the deviation is related to their metallicity. Here they also gives an empirical fit between the deviation and the metallicity. So we put IZW18 also in this plot, which is shown here. So it follows actually very well with this empirical relation. And this is also one of the reasons why we believe this 3.5 marginal detection could be very likely a real detection. So on the other hand, as I introduced and as also discussed by Susan Maiden, is that at very low metallicity, CO molecules will be destroyed easily and into singly ionized carbon. So this is also found in the observations that metal poor galaxies, they show very high C+ over CO ratio compared to the normal star-forming galaxies, almost 1 magnitude higher. So we use the data from Cormier 2015, the C+ data, to also derive this ratio for IZW18. We found that IZW18 shows an even higher ratio compared to the other metal poor galaxies. And in general, these galaxies, they show a very well correlation with the metallicity and also a mild correlation with specific star formation rate. So this means that these galaxies, they show a large amount of CO dark gas. And CO may not be an ideal tracer for the metal poor galaxy for the molecular gas. Instead, C+, despite of various caveats, can be a better tracer of the molecular gas. Then I used the calibration between LCO to molecular gas introduced by, again by Susan, to derive the alpha CO and put it back in this plot. We found that first, the alpha CO is also very high, above 2000, but it does not follow the trend defined by the dwarf galaxies here, the red dashed line. But if we extrapolate the other relations in this plot, they can more or less explain the position of IZW18. And finally, I want to, because we use the interferometry data, we got not only the spectra, but also the continuum at 1.3 millimeter. So for IZW18, because previously there was no observation in the sub-millimeter regime at wavelengths higher than 160 micron. So these 3 sigma upper limit at 1.3 millimeter indicates that actually there is no sub-millimeter excess in the SED of IZW18, which is different from what is always observed in other dwarf galaxies. And on the other hand, it can also put some constraints on the radial regime. We can see that the slope here is steeper than the slope defined by the existing radial observations, which means that the free emission, the fraction of free emission at 1.3 millimeter is actually very high compared to the synchrotron radiation. So I leave my summary here, and that's all for my talk. I will take questions. Thank you.
Thank you very much, Luwenjia, for this interesting talk. Very interesting results on a peculiar galaxy. So we have some time for questions. Please feel free to raise your hand or type in Slack. Anita Zanella.
Hi, thanks for the talk. About the detection that you were showing, I was wondering, it seems maybe narrow to me. So I was wondering how the width of the line compares with the width of other lines, for example, the C2 line, whether that's comparable or not.
The width we can see here is really narrow, around 15 kilometers per second. But actually, I haven't checked the C+ line. I should. In my impression, I have the impression that yes, indeed, it's quite narrow compared to the C+ line. I need to check that later.
Okay, thanks.
All right, thank you. I encourage everyone to follow up with your questions in the Slack channel. Thanks, Luwenjia. Our next speaker is Vianney Lebouteiller from CNRS CEA, telling us about Paris multi-phase, multi-sector ISM modeling techniques for unresolved galaxies.
Thanks, and thanks to the organizers for allowing me to present this contribution. So I'll present a summary of multi-phase and multi-sector ISM modeling techniques we've been using in our team that are adapted to spatially unresolved galaxies. And for the science application, I will try to focus on the influence of compact objects in dwarf galaxies. The second part of the talk is and the new results and the tool we've been developing was done together with Lise Ramambason, who talked earlier. So the motivations are numerous, but basically it's partly motivated by the fact that HeII galaxies start to reveal the expected same complex distribution of matter and phases that we've been seeing in nearby galaxies, especially with Spitzer and Herschel spectral lines. And this is well illustrated by these observations of C2 and O3 at very high redshifts. It's only two lines, C2 and O3, but it's already two lines coming from different phases. So to interpret such an observation, you already need multi-phase models. But there is a more general need to interpret spectra of unresolved sources, especially unresolved, whether they are HeII optical spectra or nearby infrared spectra, nearby galaxy infrared spectra, which are often unresolved. But also we want to possibly reach the simplest description possible of the ISM that will enable meaningful diagnostics and meaningful statistical trends. And so the ISM is filled with interesting diagnostics, of course. Some of them depend a lot on the ISM structure, some of them depend less. So those that depend less, it's the metallicity, the star formation rate, ionized gas mass. You would more or less get the right answer, or the same answer, I should say, depending on the various hypotheses you can use for the ISM structure. But some of them depend a lot on the ISM structure, like the escape fraction of ionizing photons especially, but also the heating rate contributions or the molecular hydrogen content or the origin of C2. And so our approach has been that of Péquignot 2008. It has been motivated by his study of 1VK18, which we just heard about. And Péquignot basically was trying to solve the difficulties, solve the problem of the high electron temperature from the optical O3 lines. And he solved it using radiation-bounded condensations in a matter-bounded diffuse medium, and introduced the concept of topology, which is basically the integrated covering factor of several sectors having similar physical conditions. And here sectors, you can see it as sight lines from the stellar cluster into different sectors with different depth, and each sector corresponds to 1D model. To a 1D model. And here I'm showing the illustration of, again, this is 1VK18. This is the northwest cluster. In yellow, you see the H-alpha emission, the stars in blue, and on top of that, a topological model with 4 sectors. But the placement of this sector is arbitrary, and I will come back to that. So that's the approach we've been using for a while now for Dwarf Galaxy Survey and specific objects. So the assumption has always been to use a single stellar population and the combination of 1D models, but I will come back to the single stellar population assumption. And because we needed to account for X-rays and dust and H2, we've been using cloudy. So on the left, it's the various iterations and the various configurations we've been using. So I don't have time to explain all of that, of course, but throughout these iterations, we've been able to gradually improve the technique by increasing slowly the number of sectors, considering matter-bounded sectors, radiation-bounded sectors, or both. Including the contribution of the X-rays and also including optical lines as well as infrared lines. So 1VK18 was probably the most complex model because we had 4 sectors and some of them were matter bounded. So we heard already about that interesting galaxy, and in the 2017 paper, what we did was to basically convert the Pequeño model with cloudy with new ingredients and constraints for the optical and infrared lines, X-rays, dust, and H2. So in the middle, you see some of the results. It's just the SCD observed and modeled. On the left, you see the X-ray component, and on the right, we see the abundances versus the depth in the radiation-bounded sector and the cumulative intensities of the lines. But basically, what I just wanted to highlight is the few important results. For instance, that the fact that C2 mostly comes from the neutral atomic gas, more than 85%. And I remind you, it's an extreme galaxy and with a very, very low dust to gas mass ratio. And then we also investigated the hypothesis that molecular hydrogen was abundant in H2 in clumps, in dense clumps, and these clumps had to be very tiny, less than 1 parsec in size, very dense, and they could hide as much as 10 to the 7 solar masses, which is as much as the H1 mass. But for that, we had used the Leroy et al. CO upper limit at the time, but I will come back to that later. But the most interesting result was probably this one, that the photoelectric effect hitting on dust grains or PHs, which is dominant in Milky Way-like conditions, and that's the usual hypothesis you would do for any galaxy by default, is not dominant in the neutral atomic gas. It's not the dominant heating, and rather it's the photoionization by a single ultra-luminous X-ray source, which is pretty well studied in this source in 1VK18. And so it's shown here in this plot where we show, as a function of the depth in the radiation-bounded sector, the heating rate of due to the ionization of neutral helium, neutral hydrogen, which are much higher than the photoelectric effect heating, and the main coulomps being C2, O1, and silicon-2 in the mid-infrared. So it has potential implications for HeII galaxies and extremely metal-poor galaxies in general, because for these you expect a very low dust to gas mass ratio, even lower than what you would just simply assume with the metallicity, because it's non-linear. But also at low metallicity, you have more high mass X-ray binaries, and they are themselves, these binaries are more luminous. So all in all, the balance tips in favor of the photoionization by X-rays at extremely low metallicities with respect to the photoelectric heating. And so it has important consequences for the origin of the C2 line, for the CO dark gas H2, possibly also the star formation quenching, because the X-ray photoionization being a much efficient heating mechanism, it can lead to warmer ISM temperatures on large scales and even long time scales. So it could be an interesting star formation quenching mechanism to take into account. For 1VK18, some of the parameters were manually tuned, and we were using a specific abundance set and specific radiation field and a specific pressure profile even. And for the automatic methods that we used for the Dwarf Galaxy Survey that Sue Madden presented before, we were using automatic methods, but always using the chi-square deterministic approach, which proved very complicated because we're not able to handle very well upper limits or able to derive reliable error bars and derived parameters. The number of free parameters, effective number of free parameters was difficult to estimate and also difficult to compare the models, hard to use priors. And so we needed a robust statistical framework. So we turned to MCMC techniques. And the key here is really to apply it to multi-picked probability density functions, because ISM grids and models that will use ISM grids have complex solutions. And so here is an illustration of what the method we've been using, which is called sequential importance sampling particle filter. So on top, you have a probability density function, which can be either your prior or a previous step in the convergence process to the posterior distribution. And then we have a large number of samples sampling this distribution. And each sample is going to go through mini Markov chains in a way. And they will be given new weights, and some of the samples will be dropped altogether. And this will give you a new distribution, and eventually it's going to converge to the posterior. And so that's the approach we've been using for this new tool called multigrid that Lise Ramambason presented, which allows us to do an inference of primary parameters in a multi-dimensional grid. So for us, it's a cloudy grid with density, emitticity, etc. But in fact, the code is completely agnostic to the model grid used. So as long as you have a list of tracers and parameters, it will work. And in the sense, it's very close to the nebula bias code, if you know it. But here, the focus is really on the combination of models and the application to the multi-phase ISM. And what we want is to make predictions for unobserved tracers and also secondary parameters that are not used for the inference. So basically here you can think of any cloudy parameter you like. And also I want to insist on the fact that we don't need to tabulate all the parameters. Some can be calculated on the fly. For instance, an extinction law parameter, which is already implemented in the code, is just calculated on the fly. It's not part of the tables. Here I'm showing an example of a potential topology with two sectors. So here's just a 2D representation of the covering factors, really. And next to it is the same plot, but with the sectors distributed randomly. And this is just to illustrate the fact that the topology is exactly the same in the two cases. So this is completely indistinguishable from the model point of view. But then next to it, what I'm showing is the same thing as here, but this time it's distributed in 3D and then projected. So we are distributing the emissivities in 3D and then projecting it a little bit like what Cloudy 3D does in 3 different tracers. And then I added the stars to make it look pretty. And this is basically what the model sees in a way, and how the best way to compare to what you think the object could look like. And really the goal is to automatize as much as possible the determination of topological parameters, including several clusters. So it's very close to that figure of Harrikan et al. 2019. We want to do that automatically. And it can include several clusters, even though most of the examples we've been working on so far have a single cluster. And this is just an example of some results. So here we have PDFs of observed line fluxes. Sorry, you cannot see the labels. Then the PDFs of the parameters. Sometimes we have two because there are two sectors. And then the fraction of the lines coming from sector 1 or sector 2. This is an ideal case. It's a benchmark case, but here's an example with a real case, real life object. This is 1VK18. So we have several dozens of lines and then a 4-sector model. And then you can see the contribution from each sector to each line. So all of that is very preliminary, but it seems to be working pretty well. The first applications concern the escape fraction of ionizing photons. That's the work that Lise Ramambason talked about already. And another objective was to reproduce the results of Pequigno and our 2017 paper in an automatic way, fully automatic way. And it's working pretty well because we're able to reproduce the ionized gas mass, the atomic gas mass, and the metallicity, of course, quantify the origin of C2, which is about 85 plus or minus 5%. This time we can put error bars on that in the neutral atomic gas. What's interesting is that most of the H2 mass, which is about 10 to the 7 solar masses again, would come from the C+ zone, which is a different result from the 2017 paper. And I think it's because in this new result here, we're using the marginal CO detection in the Zhou et al. Paper. And then the covering factor of the CO emitting sector is 5%. So we still need to translate that into physical size. And then we have other parameters under investigation. I just want to emphasize the fact that here these results don't use a specific abundance set or radiation field use, so it's pretty promising. And this is my conclusion. So topological models are really useful tools. And you can wonder how far we can really go with the combination of 1D models and not why not use 3D models. So there are plenty of things to talk about that. So I don't have time to say it here, but basically we just need so far to go beyond simple single 1D models. And the improvements that we have by having several sectors largely compensate for some secondary effects like reflected lights, for instance, between the sectors. And anyway, we're going to consider other configurations in the future. And then for the prospects, so for 1VK18, we have some H2 predictions and Neon 5 predictions we would like to test. So we would really love to have a JWST observation for that. For the Dwarf Galaxy Survey, there is the escape fraction we're working on, and the next projects will tackle the influence of X-ray sources on the ASM properties and the amount of CO dark H2 gas. So do in an automatic way what Sumadan presented. And then as far as the models are concerned, well, we want to release the code and the associated cloudy grids very soon. And also we're trying to improve it as we speak by implementing power law distributions for the parameters along with Chris Richardson, which is going to speak on Friday, and also infer from the ISM signatures, infer the radiation field shape, a little bit like what Hiroya Umeda showed, but this time accounting for several sectors. That's it. Thank you.
Thank you, Vianney, for interesting talk. Very useful tools. Looking forward to see the prospects with James Webb observations. Unfortunately, we're out of time for questions, but I'm encouraging everyone to write their questions on Slack. The final talk of this session, Mahda Gholami from IPM. She'll be talking about another interesting local galaxy, IC.
Thank you. Could you see my slides?
There is a little bit of lag. No,
yes,
it's your. Okay, now we can. Yes, perfect.
Okay, thank you. I want to talk about the big survey that we are working on this survey these days. We have conducted an optical monitoring survey in nearby dwarf galaxies in the local group, and the dwarf galaxy that I'm working on it is IC10. I must at the first show you that the map of our sample of galaxies that, as you can see in this map, the red circles are the dwarfs of Milky Way, and the blue triangles are the dwarfs of the Andromeda, and isolated dwarfs are shown in green. So we observed using Isaac Newton telescope with wide field camera in two bands of I and V. And our aim of this survey is identifying the AGB stars and red supergiant stars at the end point of their evolution, because they are good tracers to find the star formation history for the galaxy. We are looking for line period variables of stars. After finding the AGB stars and red supergiant stars, we are looking for line period variable stars to know that the pulsation of instability pulsation of this kind of stars and the age of these stars and the mass of them to reconstruct the star formation history about them. So you can see the table of our observation of IC10 dwarf galaxy. I'm working on IC10 in this sample. And we have between June 2015 to October 2017. And after that, the images that obtained using INT telescope with wide field camera has contains of four CCDs that you can see that it needs some processing. Tele is the pipeline for optical images that you can combine CCDs if needs some. It applies some changes on the image of CCDs, and you can find the images as you can see at the right slide. And because we are sure that our galaxy is very small and is located at the center of the CCD4, we just try to analyze the CCD4 at our images. And after that, at the previous slide, I was added that we did all of the analysis with the photometry code, with STSON code, that it makes us a catalog of stars and stars of the IC10, that the coordinates of the stars at the image with magnitudes in each band is, I told you before, we are looking for line period variables. So we have a catalog of stars that each star has maybe has some variability during the time of the observation. So we must separate the non-variable stars with variable stars. To do that, we plotted the histogram of the L index. What is L index? L index is the variability number that our code calculated this variability index for each stars. And we know that all of the variable stars have the minimum number of L index. And if we follow the L index for each star, we can find that each of the stars is variable or non-variable. As you can see, we fitted a Gaussian function on each histogram to find that the non-variable stars are located at this Gaussian fit, and the variable stars are exceeded at the following of the fit of Gaussian. So I show the green dotted line that L index is 2. It means that all of the stars that has all of the stars that have L index of 2 variable stars versus I magnitude, and the high color that we can dotted line is AGBT. AGBT is the places that the AGB stars are at the brightest form of a star. And after the line period variables, after the variable stars are recognized in our catalog, we are trying to find the contamination for this galaxy, because the IC10 is located at the galactic plane and is contaminated with the Milky Way stars. So for analysis of this galaxy, we need to remove the contamination. For example, we tried to using the Gaia catalog, and because the Gaia catalog contains of all of the Milky Way stars with proper motion and parallaxes, so we use the parallax and proper motion for each star to find that the foreground stars in our catalog, and then remove them from our catalog. You can see the red dots at our plot that they are foreground stars using Gaia catalog. And at this plot, you can see the magenta dot on our plot that it is the simulated one. We tried to find the foreground stars using both Gaia catalog and simulation. We must understand that the simulation foreground stars, the manner of the foreground stars in the simulation one, how it involve our plots, how it involve our stars in this galaxy. And we found that the location and the reddening of the three-legged simulation stars are at the good match with the Gaia stars. You can see the Gaia stars that are foreground stars for our galaxy at the bottom of the slide. And so we remove the foreground stars from our galaxy catalog, and then at this time we are sure about the variability of our stars, that we separate them from the non-variable stars. After that, we, as I told before, we are trying to find the line period variable stars because of their instability in pulsations. We can find a star formation history for this galaxy. We plotted the magnitude, the amplitude of variety in I band versus I band and versus color for the variable stars. We know that the line period variable stars have the amplitude in I band more than 0.2 magnitude. So we overplotted a red dotted line, as you can see at the bottom of the plot, that recognize 0.2 magnitude. And the stars with the amplitude more than 0.2 magnitude are the candidates for the line period variables. We separated the line period variables both in amplitude and both in I. We TV marked them on the image and tried to find the saturated stars and separated the bad stars or bad pixels from our image. And then finally, we find that 454 variable stars. Our catalog contains 53,580 stars, and finally I highlighted the line period variable stars in green in this plot. At color magnitude diagram, we can see that the location of the line period variable stars are the top of the isochrones. The isochrones are shown at this plot from the marigolds at constant metallicity, and you can see the line period variable stars are located at the red color, and you can see the red dotted line that is about the 23 magnitude in I band, and it is the completeness limit that we try to find the completeness limit for our stars in our catalog at the first time after the photometry process, because we must know that at which magnitude our photometry is accurate enough and we can trust our photometry. So we added some artificial stars in our one of our image and tried to recover them by our code. And we plotted the completeness of the recovering of these artificial stars in our image versus the I band magnitude and V band magnitude, and find that until around 22 magnitude in I band and V band, the most of the artificial stars are recovered, and we could find them in our image using our photometry method. So the completeness limits for the I band magnitude that is shown with the black line is 23.07 magnitude, and for the V band 23.66 magnitude. That the completeness limit is the location of the plot that the 50% of the stars are recovered. At least 50% of the stars are recovered. So we overplotted the completeness limit on our CMD in our analysis. You can see the line period variable stars that, yes?
Sorry to interrupt. We need to wrap up.
Okay, yes, thank you. You can see that we highlighted the line period variable stars on our images, and finally, for the time I must summarize my tagging. Our aim of finding line period variable stars is finding a star formation rate for the IC10 dwarf galaxy. We know that the star formation rate for this galaxy is very high, and we can find that the star formation rates for this galaxy at different metallicity. And you can see that with increasing the metallicity, you can find a star formation more star formation rate for this galaxy. And we are trying to find that these days. We are trying to find that what is the fluctuation of this galaxy, because we know that this galaxy is an isolated galaxy, and we don't know why this galaxy is a high star forming galaxy. It is finished. Thank you.
Thank you very much for your interesting talk. We are out of time for questions, but please everyone follow up with the in Slack channel. I want to thank, maybe Matilde, you can stop your screen sharing. Thank you.
Yes, of course. Thank you.
Everyone, all the speakers of this session for their interesting talks. It is now time to look at posters, interact. Please join the breakout rooms. This will be the end of the session today, unless Yuki have some announcements for tomorrow, or otherwise we can all join breakout rooms and continue the discussions.
Yeah, I don't have anything special.
Okay, great. Thank you, everyone. See you in the breakout rooms, and then tomorrow continuing our meeting. Have a nice day or night.